So this lecture is going to be a brief introduction to the concepts of drag and lift. I'm going to go pretty quickly through this, and you can take your time to read back through it, watch some of the other videos. I'm assuming you've already watched the video with the people in the skydiving tunnel. And thinking about what's happening there, you've got gravity pulling those people down. And then what's holding them up? What's holding them up is the drag force that the fluid is exerting on them in the direction that it's flowing. And thus, we can define our drag force here in the top line as the force a flowing fluid exerts on a body in the direction of flow. All right. So, let's make that red. We have a flowing fluid. It's exerting a force on the body in the direction of flow. We'll talk in a minute about why that happens. The lift force, which we'll talk about lift later on, is going to be the sum of the components of the pressure and wall shear forces in the direction basically normal to the flow. And we'll go to red, normal to the flow. So we've got fluid flowing around an object. We've got forces that we're going to resolve into two components. One that is in the direction of the flow that we're going to call the drag force, and one that's normal to the flow that we're going to call the lift force. So you can see here this airfoil that this guy, fun little tools, and around that guy you have shear forces that are kind of going along the airfoil, and you've also got pressure distribution that's developing around it. And so you can see then up to the upper right of it here, the normal vector that we're going to call lift, and we've got the parallel vector that we're going to call drag force. And in reality, there's a big distribution of forces that are going to develop around this thing. And it's very difficult to handle those sort of distributions. You would have to integrate over the whole surface what these forces look like to get a real accurate number. And so we'll see in a minute that we're going to use coefficients to simplify that, as we've done in the past. And so again, here looking at the stresses and the stress distribution here on the wing, you've got these stresses normal to the surface, which are going to be a result of pressure differences. And then you've got stresses tangential to the surface, which are due to wall shear. And I'll draw a little diagram in a minute that's going to highlight that a little bit better. But I want to get specifically to the equations for drag coefficients and lift coefficients. So for those guys, again, we're going to replace some of the difficult integration with coefficients of drag and coefficients of lift. And so the overall drag coefficient is defined it's not working. Hang on. There we go. Got it working. Defined this way. So C sub D is the drag coefficient, and that's equal to the force of drag, F sub D, over 1/2 times rho, the density, times V squared over A. V squared A. We'll talk a minute about what that A is. Whereas the lift coefficient is going to be defined very similarly, but instead of the force of drag, we're going to use the force of lift. And instead of C sub D, we're going to use C sub L. But otherwise, it's the same equation. And so we'll talk about these C sub D and C sub L in a minute. But the other thing that's important here is that A is the frontal area when we're talking about most objects, especially when we're dealing with drag calculations. It's the area seen from in front of the body. So as you've got your surface and you've got your fluid flowing at it, the frontal area that it sees is what you're going to plug in for A there. V is the free stream velocity, which is located far away from the body, not right at the edge where there's no slip, but far away from the body. But for thin bodies like airfoils, wings, instead of using that frontal area, when it's oriented pretty much like this, the A we're going to use is actually the planform area. Okay, the planform area is what is the area as seen from above the body. All right, so both the drag and lift coefficients that you look up in tables assume that you're using A correctly. And for the most part, we're going to use frontal area for most objects, unless it's a wing, and then we're going to use that planform area. So we just defined the drag coefficient and lift coefficient up above, but in reality, this drag that we're experiencing is a combination of drag due to what we call friction drag, which is that skin friction drag, the wall shear stress, as well as pressure drag, or what we call form drag. And that's going to be due to the fact that if you have an object here and you have a moving fluid hitting it, you're going to experience a higher pressure on this side of the object than you experience on the back side of the object. And because there's a higher pressure here than here, and they're both pushing on the same cross-sectional area, you're going to have a higher force here than you have here. And that way you have a net force this way, and that's where you get the pressure drag from. And so we can break that coefficient of drag into the part due to friction as well as the part due to pressure. But in reality, it's difficult to distinguish between the two. Our measurements that we make of force when we're doing experiments don't distinguish between these two. And so we lump them into one, as we showed above, an overall drag coefficient. But because of that, we have to be really careful with our coefficient of drag and our coefficient of lift later on, because it's going to be specific to the way the body is oriented. If we have an object that's oriented like this, we're going to have a bigger difference in pressure between this side and this side, assuming the fluid's going this way, than if it's oriented this way. This way it's more streamlined, and you're going to see the flow go around here, and the difference between pressure on this side and this side is going to be a lot less. And so that in order to account for that, we need to have our drag coefficients be specific to the orientation of the object. Okay, so the more parallel the surfaces of flow, the greater the contribution of friction drag is to the total drag. If a surface is generally parallel to the flow, the pressure drag is going to be low or nearly zero. If the surface is perpendicular to the flow, then the total drag is almost completely due to the pressure drag. And so another way of thinking about what I was talking about before with the pressure difference on both sides is that if the pressure on the front is greater than the pressure on the back, the force due to the pressure is equal to that area times the pressure on the front minus the pressure on the back. Okay? So because we don't distinguish between these two types of friction drag, we get this overall C sub D. You can see on this plot here for this wing, the friction drag as a function of how D over L, what shape this wing is, and then the pressure drag also as a function of it. And then you can see the total drag, which accounts for both of them, up there on the top. So the lecture is going to continue on the next video. Open the next video from the file and we'll pick up there.